Hello, welcome to this learning module. In this video, we're going to take a brief pause and talk about UV-vis spectroscopy, ultraviolet and visible light spectroscopy. It's not directly related to IR, but it is something that we need to cover. It won't take us very long because it's really not the most important tool in organic chemistry, but we need to talk about it anyway because it has some implications for organic molecules. Now, you may have done UV-vis spectroscopy before, maybe in a high school chemistry class or in Gen Chem class. You may have used an instrument called a Spec 20 to look at solutions that had a color of various intensities, and you were measuring the intensity of that color using a Spec 20, looking at the absorbance of a particular wavelength of visible light. That would be UV-vis spectroscopy. In organic chemistry, we're going to use it to talk about conjugation, really just one specific area of chemistry, the concept of conjugation. So let's take a trip over here for a minute and talk about pi bonds. So pi bonds are carbon-carbon double bonds. And what you need to know about pi bonds is that pi bonds absorb light. Pi bonds absorb ultraviolet light. And more pi bonds in conjugation, we'll talk about that in a second, absorb longer wavelengths of light. Those are the three key concepts you have to keep in mind for UV-vis spectroscopy as it pertains to organic chemistry. Okay, so with that as our backdrop, let's take a step back for a second. You may recall a diagram that looks something like this from a chemistry course, where you have a hydrogen atom with its electron and a hydrogen atom with its electron, and those two atomic orbitals combine to form a molecular orbital and a molecular bonding orbital and a molecular antibonding orbital. This we would call the sigma bonding orbital, and this one we would call the sigma star anti-bonding orbital. This is how bonds are formed. These two s orbitals in the hydrogen atom overlap to form the bonding orbital, or they overlap to form the anti-bonding orbital. You may have seen a diagram like this before. I'm not going to go into all the details of this. It's not really important for what we're doing right now. But what we need to know is that anytime two atoms combine to make a bond, the orbitals from each of those atoms, one orbital from each of those atoms, overlaps to form a lower energy bonding orbital and a higher energy antibonding orbital. So our y-axis here is relative energy. So it's more stable for the electrons to go into the sigma bonding orbital, and less stable should they go into the sigma star antibonding orbital. That's all I really want to say about that right now. Okay, so when you have a molecule, let's just take a molecule, doesn't really matter, just make it a long straight chain molecule. There are lots of bonds in this molecule. There's lots of carbon-carbon bonds, but remember, every carbon has enough hydrogens to make 4 bonds, so there are lots of carbon-hydrogen bonds as well. So there's lots of bonds in this molecule. And I'm going to add one pi bond for now. So what we need to know for the molecular orbital for this molecule, for every bond in this molecule, every carbon-carbon bond, every carbon-hydrogen bond, there is a diagram that looks like this diagram on the left, where the carbon and hydrogen are forming a bond together. The 2 electrons go in the bonding orbital, and there's an antibonding orbital as well. The same is true for a larger molecule. There's just a lot more of them. With these diagrams, one more thing to orient you to, there is an unspoken line right through the middle of the diagram, and we kind of call this the non-bonding energy. It means what it says it means. It's non-bonding energy. It's the energy of the atoms as if they had not been bonded together. The electrons are more stable when they are bonded together, but had they not been bonded together, the electrons have the energy at the non-bonding level. Whenever you form bonding and antibonding orbitals, those bonding and antibonding orbitals are always symmetric about the non-bonding level. That means as stable as the sigma bonding orbital is, the antibonding orbital is an equal amount unstable. It's symmetric about the non-bonding level. As far down as you go below, you have to go the same distance above. every sigma bond, every bonding orbital has a corresponding antibonding orbital that's equal in energy but above the non-bonding level. So when you have a more complicated molecule, there are lots of sigma bonds in this molecule. So we'll start by drawing our non-bonding level right here in the middle. The sigma bonding orbitals are the most stable. So there are lots of sigma bonding orbitals for every carbon-carbon bond and every carbon-hydrogen bond. Because the antibonding orbital is symmetric about the non-bonding level, if there's all these sigma bonding orbitals for the CC and CH bonds, there must be an equal number of sigma antibonding orbitals at an equal distance above the non-bonding level. Don't worry about how all this happens. I haven't quite gotten to UV vis yet. Just follow along with me so far. Sigma bonding orbitals are the most stable, so they're the lowest in energy. That means the antibonding orbitals are the highest energy, least stable orbitals. All of the sigma electrons in this molecule, all the electrons in these carbon-carbon bonds, in these carbon-hydrogen bonds, all of the sigma electrons would be down here in these sigma bonding orbitals. There's one pi bond in this molecule. So what you need to know is that pi bonds are higher in energy than sigma bonds. So then where would the pi star orbital be? The orbitals are symmetric about the non-bonding level, so if the pi star is higher in energy, if the pi bonding orbital is higher in energy, then the pi star anti-bonding orbital must be lower in energy. And the electrons in this pi bond then are here in the pi bonding orbital. Okay, so all that now is a setup for ultraviolet UV vis spectroscopy. What I want you to notice is that there is a discrete distance between the pi orbital and the pi star anti-bonding orbital. And if the y-axis is energy, then there's a discrete energy difference between these orbitals. You've probably heard this concept before. Energy orbitals are quantized. The 1s, the 2s, the 2p, the orbitals are quantized, meaning that there's a discrete amount of energy that corresponds to each orbital. And so if you want to, let me rephrase. So if a photon hits this molecule, the energy in that photon could be transferred to the molecule. And if that energy is exactly the right amount of energy, it could excite one of these electrons up to the pi star anti-bonding orbital. In order to do that, the photon would have to have exactly this delta E amount of energy. Orbital energies are quantized. It would require exactly that amount of energy to excite the electron up to the higher energy level. If the photon has any other energy, then it would not excite this electron. So what that means is that for every molecule, there's one photon of one specific energy that has exactly the right amount of energy to excite an electron up to the pi star antibonding orbital. Energy is related to the frequency of the photon and the wavelength of the photon. And for pi bonds absorb energy in the ultraviolet range of the electromagnetic spectrum. It absorbs ultraviolet light, fairly high energy photon, which means it's a fairly short wavelength and a fairly high frequency. This is true for pi bonds. This delta E happens to be the amount of energy associated with an ultraviolet photon. So when an ultraviolet light of a very specific wavelength hits a molecule with a pi bond, it can absorb that energy and excite the electron to the pi star antibonding orbital. And we end up with a spectrum that looks something like this. So notice that isoprene, in this case, has 2 pi bonds. I'll talk about that in a second. And so this wavelength here, which they're telling us is 222 nanometers, is the energy required to excite the pi electron up to a higher energy level. That one energy level, that photon with exactly that amount of energy, we call lambda max. Lambda max is the wavelength of light that is perfectly situated to excite an electron to a higher energy level. It's a wavelength of light that has exactly the right amount of energy to excite the electron to the higher energy level. Any other wavelength of light does not get absorbed by the molecule and is not used to excite the electron up to a higher energy level. Okay, so that's thing one. The next thing, as you add more pi bonds to the molecule, the next pi bond is a bit higher in energy. That's one of the things that's true about pi bonds. As you add the next pi bond is a little bit higher in energy. What then does that mean about the pi star orbital? If the pi orbital is a little bit higher in energy, the pi star orbital must be a little bit lower than in energy. And the same would be true for the next pi bond. As you add the next pi bond would be a little bit higher in energy, and the next pi star would be a little bit lower in energy. This is true if the pi bonds are in conjugation. What does in conjugation mean? It means that they are connected to each other through resonance. It means that there is this pattern of pi, sigma, pi, sigma, pi, sigma. There's this pattern of every other bond is a pi bond with one single bond in between, and no sp3 hybridized carbons in the middle. I could draw a resonance contributor where I take these electrons, move them over here, these electrons move them over here, these electrons put them onto this carbon. I can draw a resonance that involves these pi bonds. This is in contrast with an isolated pi bond. So if I were to add another pi bond over here, it's a very nice pi bond, but it has nothing to do with the three that I've already drawn. It is an isolated pi bond, so it would not go with this analysis. This analysis only works if the next pi bond is in conjugation. So the next pi bond there wouldn't help. But if I put the next pi bond in conjugation with the system, then that does fit this analysis. The next pi bond will be a little bit higher in energy, the next pi star will be a little bit lower in energy, and I can continue this pattern. Why does that matter? Look what happens to this delta E then as you add more and more pi bonds in conjugation. That delta E gets smaller. And if that delta E gets smaller, that means that there's less energy needed to excite the electron to the pi star antibonding orbital. So think that through for a second. If there's less energy needed, and if one pi bond absorbs ultraviolet light because the energy gap is in the ultraviolet range, as I add more pi bonds in conjugation, if less energy is needed to excite the electron, does that mean that I'm going to need a photon of a longer wavelength or a shorter wavelength than when I only had the one pi bond? Now that I've got 4 in conjugation and this delta E is smaller, less energy is needed to excite the electron. Does that mean that compared to the case where we only had the one pi bond, am I going to need a longer or shorter wavelength photon to excite the electron? Take a second, think about that. If delta E is smaller, if I need less energy, then I need a photon that is less energy than the case where I only had the one pi bond. Less energy is a longer wavelength photon. So if delta E is now smaller and less energy is needed, that means I need a longer wavelength photon to have exactly the right amount of energy to excite the electron up to the pi star antibonding orbital, or a slightly lower frequency photon. Okay, so then the next question, if I need a slightly longer wavelength photon, a slightly lower frequency photon, and I'm starting in the ultraviolet range with one pi bond, as I add more pi bonds, the longer wavelength photons are going to move closer to what? The X-ray range of the electromagnetic spectrum or the visible range of the electromagnetic spectrum. If the less energy is needed, if I need a longer photon, a longer wavelength photon, is that going to move me more towards the X-ray section of the electromagnetic spectrum or the visible spectrum? So if you remember what we did with the electromagnetic spectrum, as the energy goes down, the longer wavelength photons who are on the right side of this diagram, they become less dangerous. So if the energy is going down and it becomes a less dangerous photon, it's not moving towards the X-ray, it will be moving more towards the visible. So as I add more pi bonds in conjugation in this molecule, delta E gets smaller. I need a longer and longer wavelength photon, a lower and lower frequency photon. And we see that here in these diagrams. So these are some sample UV-Vis diagrams. A couple of things to point out. Here, notice that the pi bonds are one carbon-carbon pi bond and one carbon-oxygen pi bond. That's fine. It doesn't have to necessarily always be carbon-carbon pi bonds. And it still has a lambda max. This lambda max looks like it's about 235 or so. So whether it's carbon-carbon or carbon-oxygen pi bond doesn't really matter. But now look at this one up here with lycopene. Notice how many pi bonds it has in conjugation. It's got lots of pi bonds. What I want to point out is that only these pi bonds are the ones in conjugation. These ones out here are isolated from the conjugated system, and so they're not part of this analysis. But notice how many pi bonds there are in conjugation. And notice what happens with lambda max. Lambda max is here at 471. And what's interesting about 471 is it's bigger than 400. And if you remember from our electromagnetic spectrum, the visible spectrum starts at 400 nanometers. So what that means is now with enough pi bonds in conjugation, the molecule lycopene is absorbing visible light. And that's very interesting because when the molecule absorbs visible light, it absorbs some of the light, it reflects back the rest of the light, and the molecule takes on a color. If you remember in organic chemistry, most of the things that we use are colorless or white solids or something like that. It's very rare to see a color, and that's because most of the molecules only absorb at best in the ultraviolet range. You need a lot of pi bonds in conjugation before you start absorbing visible light, and the molecule takes on a color. And that's what I want. That's the point I want to get across in this video about UV-Vis spectroscopy. Remember our 3 points. Pi bonds absorb light. Pi bonds absorb ultraviolet light. More pi bonds in conjugation absorb longer wavelengths of light. Eventually, with enough pi bonds in conjugation, this delta E gets small enough that the photon gets long enough that the energy is low enough that you absorb a visible photon of light. And when you absorb a visible photon, then you reflect back the rest of the visible photons, and the molecule takes on a color. And that's very interesting. Roughly speaking, again, this is very rough, but roughly speaking, about 7 carbon-carbon pi bonds in conjugation. About 7 pi bonds in conjugation is what you need to absorb visible light. That's not a hard and fast rule. There are exceptions all over the place, but roughly when you get to around 7 carbon-carbon pi bonds in conjugation, then you can assume pretty well that the molecule absorbs visible light. So when you look back over here at lycopene, it's got way more than 7 pi bonds in conjugation. Lycopene is a molecule you may recognize. It's in tomatoes. It's what gives tomatoes its red color. It has a very closely related molecule, beta-carotene, and beta-carotene is also highly conjugated like this, and that's in carrots, and it's what gives carrots the orange color. There's so many pi bonds that it is absorbing some of the light, and for lycopene, it's reflecting back the red. For beta-carotene, it's reflecting back the orange, and those are the colors that we see when we look at those fruits. So that's all I want to say about UV-Vis. It's not something that we're going to use very often. You just need to keep these 3 points in mind. I'm going to come back to those points many times throughout this course, and as you go on to other courses, this is something you'll need to know. Pi bonds absorb light, pi bonds absorb ultraviolet light. More pi bonds in conjugation absorbs longer and longer photons of light. Eventually, you get enough conjugation that the photon is low enough energy that it breaks over into the visible spectrum, and then the molecule takes on a color, and that's very interesting.